Well, good afternoon, ladies and gentlemen. My name is Nigel Peake. I'm the head of the Department of Applied Mathematics and Theoretical Physics here in the university, and it's a really great pleasure to welcome you to this, the 13th Andrew Chamblin Memorial Lecture. So just a few words about Andrew Chamblin first, and then a few words about today's speaker. So Andrew Chamblin was born in 1969 in Lubbock, Texas, and as after a brilliant career as an undergraduate physicist at Rice University, he moved to Oxford for a year and studied twistor theory with Roger Penrose before coming to Cambridge and St. John's College to do his PhD supervised by Gary Gibbon and Stephen Hawking. His thesis title was Aspects of Topology in Theoretical and Quantum Gravity, and he then held a very distinguished position of Draper's Research Fellow at Pembroke College. And after a series of further research positions in the UK and the US, he became assistant professor at the University of Louisville. Andrew died suddenly and unexpectedly on the 6th of February 2006 at the tragically young age of 36. And at the height of his academic powers. His family and friends and colleagues from all over the world came together to create this annual lecture together with an organ recital in Oxford to commemorate Andrew's memory. So my department is hugely proud of Andrew, and we're delighted to stage this lecture each year, and we've always been able to attract one of the world's greatest theoretical physicists to give the lecture, and this year is absolutely no exception. So John Ellis is the Clerk Maxwell Professor of Theoretical Physics at King's College London. He completed his PhD in DAMT, actually in Cambridge, and then after postdoc positions at Stanford and Caltech, he went to CERN in 1978 and held a series of positions there, including as head of the theory group. He's famed for his work on phenomenological particle physics and the connections with astrophysics, cosmology, and quantum gravity, and he's also exceedingly well known for his very popular lectures on science. He's received many awards and honours, including the Maxwell Medal and the Paul Dirac Prize from the Institute of Physics. So we're really grateful to you, John, for agreeing to come today to give this lecture, and we're very much looking forward to it.
Okay, well, thank you very much for the introduction, and thank you very much for the invitation to give this lecture, which I regard as a great honour. 1969 actually was the year in which I wrote my first research paper, so it's a long time ago. Anyway, my inspiration for the title of this talk is taken from this famous painting by Paul Gauguin. So these people are asking themselves some very basic questions about us and our place in the universe. If I translate from the French into English, what are we, where do we come from, and where are we going? So this sounds like a rather ambitious title for a talk basically about particle physics and cosmology, but my claim is that that's what we particle physicists and general relativists do. That's our job. We are lucky enough that at least sometimes people pay us to at least ask these questions, and every once in a while we hopefully provide some answers. So what is the setting for asking those questions? What do we know about the evolution of the universe? So there's this picture which some of you may have seen before in various different forms. So it tells us that the universe that we can see apparently originated in some sort of Big Bang 13.8 billion years ago, and it's now expanded to a visible size of something like 10 to the 28 centimeters. So the first task of us particle physicists is to try to understand what the stuff in the universe is made of. and this will be a large part of my talk. So that, for me, is the physicist's counterpart of the what are we question. But looking at this picture, then, of course, there's another question, which is, what happened at the beginning, or what happened in the first stages after the Big Bang? And that, for me, is the question, where do we come from? And where are we going? That, of course, is the question, what is going to happen to the universe in the future? And I'll have something to say about all three of these questions during the course of my talk. So, Gauguin formulated these questions originally in French, translated into English. Now let me be a little bit more formal, translating them into the language of particle physics. So what are we becomes the question, what is matter made of? And I would argue that a very key aspect of that question is, why do things weigh? More particularly, why do particles weigh? Because without masses for elementary particles, there could be no atoms, life would be impossible, and so on. So I think we've at least made some progress in particle physics in recent years in answering that question. Where do we come from? Well, clearly one aspect of that is, what is the origin of the matter in the universe? So there we have various ideas about the mechanisms that might have enabled matter to be created in the early universe, although we're still trying to flesh out the details of that, as I will also discuss later on. You probably know that in addition to the visible matter in the universe, the astronomers tell us that there must be a larger amount of invisible dark matter. And that could very well be made up out of particles that we can hope to detect in our experiments. Where do we come from? Where are we going? So how does the universe evolve? Well, we know that it evolves according to Einstein's equations, but on the other side of his equations, you have to put in the right form of matter, so that brings us back to particle physics. Why is the universe so big and old? What is the future of the universe? So, as I said, it's our job as particle physicists to at least ask those questions, and I'll give you some sort of a progress report as to where we are with providing a few of the answers and asking the rest. So, the answer to what is matter made of, the visible matter in the universe, the answer to that was basically completed with the discovery of the Higgs boson a few years ago at CERN, and I'll describe that. But that leaves many other open questions, the ones which I've outlined in green here, and these for sure require physics beyond our current understanding of what we call the standard model of particle physics. And those are questions that we're now, at least in some form or another, addressing with experiments of the Large Hadron Collider, the LHC, at CERN. Okay, so now let's look a little bit more at various different scales in the universe. So this is a sort of slide rule, if anybody here is old enough to remember slide rules, which takes you all the way from the size of the visible universe today, 10 to the plus 28 centimeters, down to the smallest scales that we theoretical physicists speculate about, something like 10 to the minus 32, 10 to the minus 33 centimeters. And then we've got various other scales along the way, the size of the Earth, the distance between the Earth and the Sun, and so on. And the human scale is sort of logarithmically approximately halfway along. So this picture here shows you Albert Einstein and his kid sister when they were about yay high. And so roughly speaking, that's halfway between the very large scale and the very smallest scale that we talk about. So of course we know a fair amount about what made up Einstein and his kid sister. We know they were made of molecules. Those molecules were made of atoms. So those atoms contain nuclei with clouds of electrons around them. And if I had been giving this talk 80 years ago, I might have said, well, the most fundamental constituents of nuclear matter were particles called protons and neutrons. Now, of course, we think that we know that the structure within those protons and neutrons called quarks. So, at the moment, we would say that the most fundamental constituents of matter are electrons and related particles and quarks. But, as I already mentioned, in addition to the visible matter in the universe, which is made up in this way, the astronomers tell us that there must be even more invisible dark matter, which might well be made of some sort of particle. If it is, it's going to have to be a sort of particle which we don't know yet, which is not described by our current theories of particle physics. So how are we going to explore that? Well, what we do with our collider experiments is to recreate the conditions that held when the universe was a fraction of a second old and try to understand the fundamental processes that occurred at that stage. So our collider experiments can be regarded in some form as an extension, a sort of super microscope, but also some sort of a super telescope. So what do we know or think we know about the early history of the universe? So as I mentioned earlier, we're made of atoms, but if you go back when the universe was less than about 380,000 years old, there weren't any atoms. The universe was too hot, too dense. There was only a plasma of nuclei and fundamental particles. If you go back when the universe was less than 3 minutes old, it was so hot and so dense that there weren't even nuclei. There were protons and neutrons and electrons and so on. If you go back when the universe was less than about a microsecond old, there weren't even any protons and neutrons. There were only their fundamental constituents, the quarks that I mentioned previously. And if you go back when the universe was less than about a picosecond old, we think that none of those particles had any mass whatsoever. So what we basically do in our particle physics experiments is recreate the conditions that occurred back when the universe was something like a picosecond old. And as I mentioned, maybe we can understand how dark matter emerged from the very early universe. Maybe we can understand how matter appeared. And it may be around that epoch too that matter originated in a way that I'll describe later on. So I'm going to be talking a lot about the connections between particle physics and cosmology. It's perhaps worth remembering that much of particle physics actually started in the early 20th century from astrophysics, specifically from cosmic rays. So these were discovered in 1912. These are energetic particles bombarding the Earth, made by astrophysical explosions. When those cosmic rays hit the upper atmosphere, they produce other particles, and many of the discoveries in particle physics in the first half of the last century were made by looking at those showers of particles produced by cosmic rays. For example, antimatter, a prediction of Dirac, was confirmed for the first time using cosmic ray experiments. But around the middle of the last century, it was realized that if you wanted to study these particles and their interactions systematically, in detail, then you would need to basically recreate those conditions in the laboratory. And that's why physicists developed particle accelerators in order to study the fundamental laws in detail. So those studies, particularly in the second half of the last century, supported what we now call the standard model of particle physics. So this was a theory that was proposed in the 1960s, in particular by Abdus Salam, whom you see here, originally from Pakistan, and by two American theorists, Glashow and Weinberg. And they made essential use of the ideas proposed by Peter Higgs, whom I mentioned earlier, and I'll come back to him in a moment, and other theorists back in 1964. So I think for some years, people didn't pay a lot of attention to those ideas. Almost nobody quoted those original papers for several years. But in the early 1970s, discoveries in particular at CERN started confirming predictions of their theory. Those predictions were confirmed in stunning precision by experiments that were done in particular at CERN in the 1990s. So just to give you an idea, if you've got a telescope, then you may be able to see a little red dot there under the 3. That's an experimental measurement, and the green line is a theoretical prediction, and they agree. Actually, that's a cheat, because the red dot has been blown up by a factor of 10 so that you can see it. That tells you how accurately this theory works. So what does the standard model contain? So it has a list of particles of matter. So I mentioned the electron. There's a heavier electron-like particle called the muon that was discovered in cosmic rays. I mentioned quarks. We now know there are 6 of them. And also I show here neutrinos. We know there are 3 different types of neutrino. That was the 3 on the previous slide, but I won't go into them in great detail. And then between these fundamental particles, we distinguish 4 fundamental interactions. So 2 of them are very familiar to everybody. Gravity, which keeps even theoretical physicists' feet on the ground. Electromagnetism, which was unified by James Clerk Maxwell in the 1860s while he was working at King's College London. And then we have, inside the world of particle physics, we have the strong nuclear force that holds quarks together inside protons, protons and neutrons together inside nuclei, and the weak nuclear force responsible for forms of radioactivity. So in some sense, these particles and their properties can be regarded as a sort of cosmic DNA encoding all the information you need to make all the visible stuff in the universe. With one exception. What you see on that slide does not explain where particle masses come from. And this is kind of important because, for example, if the electron didn't have a mass, then it would always travel at the speed of light, and it would never bind with nuclei to make atoms. So atoms only exist because particles can acquire a mass. So why do things, or more particularly why do particles weigh? So we physicists, of course, know why things weigh. They weigh because of Newton and Einstein. Weight is proportional to mass. W is equal to mg. So g, that's gravity. So Einstein gave us the theory of gravity. He also gave us E equals mc squared, so he related energy to mass. But those distinguished gentlemen somehow forgot to explain where the mass comes from in the first place. And that's where Peter Higgs and other theoretical physicists come in. So here you see a picture of Peter Higgs looking very distinguished, and behind him on the blackboard you see his theory. And you don't have to memorize what's written on the blackboard because it's written out in gory detail on my pullover. So the top line, that is Maxwell's equations, so the fundamental interactions. The next line is how electromagnetism and other forces act upon the fundamental particles of matter, so you can think photoelectric effect. The third line, that's how the idea of Peter Higgs gives masses to fundamental particles of matter. And the bottom line, that's how it gives masses to the particles responsible, the very heavy particles responsible for weak interactions. So there you are, it's all there. And whenever I wear this pullover, I seem to be stopped by Japanese gentlemen in elevators who want to ask me what's going on. So it's a good publicity tool. Now, a key aspect of this theory is that, well, there's this thing called phi here, which is a field permeating all of space, and just as the electromagnetic field has an associated quantum, the photon, there should be a quantum associated with this Higgs field, and that's the Higgs boson, which became, in some sense, the particle physicists' holy grail. And just mentioning that Peter Higgs was a student at King's College London, although unfortunately he had the poor taste to move somewhere else to do his famous work. Okay, so I'm not going to go through the mathematics of the pullover, but I would like to give you a physical analogy which may give you some idea of how the Higgs idea works. So I mentioned that this thing phi is what we call a field, electromagnetic fields all throughout space, gravitational fields. There's another field, the Higgs field. So differently from electromagnetic and gravitational fields, which have sources like electric charges or like the sun, the Higgs field is supposed to be absolutely homogeneous, isotropic, constant throughout the universe. So I like to compare it to Siberia in the middle of winter. Think of this enormous field of snow as far as the eye can see in all directions. So if you're a particle trying to cross this Higgs field medium, it's like somebody trying to cross Siberia. And if you're lucky, you're going to have skis, you're going to go very fast because you don't sink into the snow. So the analogy would be with a particle that does not interact with the Higgs field, doesn't have a mass, it travels at the speed of light, like the photon, for example. Or maybe you're trying to cross Siberia in snowshoes. In that case, you will sink into the snow, you will interact with that Higgs snow field, go slower than the skier, that's like a particle that goes at less than the speed of light because it has a mass. And then finally, maybe you're trying to cross Siberia in your boots. In that case, you're going to sink very deeply. You're going to go very slowly because you have a very large interaction with that Higgs snow field, particle with a large mass. So that's the basic idea. Your mass, if your particle, is related to the strength of your interaction with this thing phi there. So what is snow made of? What's the quantum of snow? It's a snowflake. And the quantum of this Higgs field is the Higgs boson, which I mentioned. Now, a snowflake, of course, comes in many different shapes, right? Because it's a composite object. Molecules of water arranged in different ways. And in fact, there's a big debate going on amongst particle physicists as to whether our Higgs boson is actually an elementary particle, which is just one of a kind, or whether there's a whole bunch of related particles, maybe because they're made up out of something else inside. So particle physics for a number of years now, and probably for a number of years into the future, is centered around this Higgs boson particle and what may lie beyond it. This is actually a picture of Peter Higgs back in 1965, 1966, when he was working out some details of this theory. And it's somewhat shaming to go back and look at his paper and see that a lot of what we've been doing ever since is already foreseen in his paper. So I'll talk about how the Higgs boson was found, what it's maybe trying to tell us, and what may lie above and beyond it. So my own personal interest in the Higgs boson started in 1975. So together with Mary Gaillard and Dimitri Nanopoulos, we thought that it was about time people started thinking about what this Higgs boson might look like in an experiment. Now, in those days, all these ideas were regarded as being distinctly speculative, and the distinguished grey-haired professors in the front row would shake their heads if you talked about the Higgs boson. And that was one of the reasons why, at the end of our paper, we said, we do not want to encourage big experimental searches for the Higgs boson. But we do think that experiments that were vulnerable to discovering it should know what it looked like. So fortunately, our advice was not taken. And the Large Hadron Collider was constructed at CERN. not just to look for the Higgs boson, but also to address others of Gauguin's questions, as I'll come back to later on. So large, 27 kilometers in circumference. It's actually in a tunnel 100 meters underground, so you don't see very much from the air. Hadron, well, that's just our jargon term for strongly interacting particles. And collider, well, yes, we make lots of collisions. So if you're lucky enough to go underground into the tunnel, this is what you see. So this is a string of magnets curving away into the distance. And inside those magnets, you have, when it's operating, thousands of billions of protons circulating in opposite directions and making collisions. So just one little anecdotal fact. Each of those protons has approximately the energy of a fly. Of course, there's so many protons in there that the energy stored in the ring is more like an airplane taking off, but each individual proton has the energy of a fly. And when it's operating, it makes billions of collisions per second, and with those collisions, we set out to understand the origin of mass, the nature of dark matter, maybe it's a particle, the primordial plasma that filled the universe when it was a fraction of a second old, and also the differences that exist between matter and antimatter, which might be linked to the fact that in the universe we see matter around us, but we don't see large amounts of antimatter. So this is a collection of pictures of the big experiments that are done at the Large Hadron Collider. These are old pictures now. These are pictures during the installation of these experiments. So CMS and Atlas, bottom left and top right, those are the ones that actually discovered the Higgs boson and now looking for particles of dark matter. LHCb, the one on the right, that's trying to understand the difference between matter and antimatter. And top left, Alice, that's the experiment which is focusing on the primordial plasma that filled the universe. And Cambridge is involved in the two experiments on the right. So just one thing that I would like to emphasize is that although these Gauguin experiments are done at CERN, they're not just done by CERN. They're in fact done by teams of literally thousands of physicists from around the world, including Cambridge. So there's something like 100 nationalities represented among the physicists doing experiments at CERN, including several hundred from the United Kingdom. Okay, so 2012 came the discovery of what we now know was the Higgs boson. And we particle physicists were very excited about it, what I can only describe as mass Higgsteria. So what were the experiments looking for? So as I said, there's billions, thousands of billions of proton collisions every second. And it works for 10 million seconds per year. So there's a lot of collisions to look at. And each of those collisions produces dozens, maybe hundreds of particles. So the curved yellow lines here correspond to charged particles, and the little blobs, those correspond to deposits of energy by neutral particles. So you have to sift through all those collisions, all those particles, and find the ones that are interesting. So in this particular simulation, you can see two big pale blue blobs on the right-hand side. Those represent two energetic particles. And there's another couple on the opposite side. And in the simulation, those particles came from the decay of a Higgs boson. That's the sort of thing that the experiments set out to look for. And in 2011, first part of 2012, they started seeing some interesting events that looked like that. So this now is a real event. This is not a simulated event. So there's a computer-generated image of the Atlas detector, those curved yellow charged particles, blobs, and you can see 4 almost straight red lines. So those correspond to 4 energetic charged particles, specifically muons, the particles that were discovered in the cosmic rays. And those 4 muons, we think, may have come from the decay of a Higgs boson. This is a picture from the CMS experiment. So here they were looking at something a bit different. So again, you see those yellow charged particles, and you can see 2 big red blobs. So those are very energetic neutral particles, because there's no track going towards them, which could be photons. And one of the things that we'd calculated back in 1975 was the possibility that the Higgs would decay into 2 photons just like that. So on July the 4th, 2012, the ATLAS and CMS experiments announced the discovery of a new particle, having convinced themselves that they were seeing not just a handful of such interesting events, but a statistically significant excess of such events that could not be explained by anything else in the standard model. So here's a scene in the CERN auditorium on that day. Lots of happy physicists, and I pay particular tribute to the guy with his back to you. That's Lynn Evans, who was the guy who actually built the LHC and made the discovery possible. And this is a picture that I like for a couple of reasons. I know what you're laughing at, but that's not what I... So the guy on the right is Peter Higgs, and the guy in the middle is François Englert, who proposed similar ideas, in fact, slightly before Peter Higgs, although he didn't specifically mention the existence of this particle. So that was in 1964, they wrote their papers. This is 2012, but in the intervening 48 years, they had never met. And I find this incredible that 2 theoretical physicists, I mean, we're traveling around the world, conferences, meeting each other all the time. They had never met in 48 years. This was the instant when they met. And then I like this picture because it shows you Fabiola Gianotti, who presented the discovery on behalf of the ATLAS experiment and went on to become now our Director General at CERN. So, no glass ceiling at CERN. Okay, so 2012, new particle discovered, but is it the Higgs boson? Is it maybe some imposter? So the situation reminded me of you're trying to complete this jigsaw puzzle. In fact, it was a jigsaw puzzle that we started in 1897 with the discovery of the electron. And there's been this missing piece for many, many years. And eventually you look in the back of the sofa and you find this bent piece of cardboard, pictures rubbed off. Is that the piece that you're looking for? So that was what we set out to study following the discovery of this new particle. So this is an analysis that I did with my then PhD student, Tivong Yu. So according to the standard model, this particle should couple to other particles proportional to their masses. So on the horizontal axis, we've got the mass of some particles. Vertical axis, how strongly the Higgs boson couples to them. And the standard model prediction is given by that red line, diagonal line, and the data, the best fit is given by the dashed line. Dotted line is this statistical uncertainty, and as you can see, the analysis is completely compatible with the standard model. So, we wrote in our paper that this particle walks and quacks like a Higgs boson. We didn't include that picture in the paper, by the way. And Peter Higgs could smile. So subsequently, this analysis has been done with much greater precision, much more accurately, much more professionally by the experimental collaborations. And so here you see a joint analysis by ATLAS and CMS. So they switched the line styles. So on our plot, the red line was the standard model. Here it's the fit. On our plot, the dashed line was the fit, and here it's the standard model. That is the same thing. The data agree with the theory. So 2013, the Nobel Prize Committee bowed to the inevitable and awarded the Nobel Prize for Physics to Peter Higgs and François Englert. And here's a quotation from the citation. "Today we believe that beyond any reasonable doubt it is a Higgs boson." And Tivong and I were very happy because that was a direct quote from our paper. But what the Nobel Prize Committee apparently didn't know was that when we sent our paper off to a journal to be published, the referee said, "Beyond any reasonable doubt" is not a scientific statement. If you want your paper to be published, you have to take that statement out. So that statement appears in the pre-publication version of our paper and in the Nobel Prize citation, but not in the published paper. So this discovery was a big deal. Without the Higgs boson, the electron would have no mass, there'd be no atoms, no chemistry. There would be no heavy nuclei. Weak interactions responsible for radioactivity would not be weak. Life would be impossible. So discovery of the Higgs boson was certainly a big deal. So is there anything else? And here I take my inspiration from James Bond, suitably modified, and I paraphrase the title of his movie, and I give you 007 reasons for claiming there must be physics beyond the standard model. So the first is that if we calculate the properties of empty space, we find it's unstable. So we find a very uncomfortable answer to Gauguin's third question. What's going to happen in the future? The universe is going to collapse. Don't believe that. I think there must be physics beyond the standard model. We also need physics beyond the standard model to explain dark matter, to explain the origin of matter, to explain why particle masses have the sizes that they do, to explain neutrinos, to explain the size of the universe, and to make a quantum theory of gravity. So, lots of things still to do, and we're addressing them with the Large Hadron Collider. So let me say a little bit about the future of the universe. Will the universe collapse? So this picture here, the horizontal axis, is the strength of the Higgs field. So it's kind of small, indicated by that red dot. But according to standard model calculations, there is another possible state with a much larger density of Higgs field. And if we were in that state, the universe would basically collapse in what we call a big crunch. Now, the problem is that according to quantum mechanics, the value of the Higgs field must fluctuate, and there is some probability that it would tunnel through that barrier. Moreover, if you go back to the early history of the universe, those fluctuations would have been much more important. And there's a puzzle as to why the whole universe didn't go immediately into that big crunch. So the answer is provided by Donald Trump. Build a wall. What you need is some extension of the standard model which erects a barrier to prevent us from going into a big crunch. And so that takes us into some sort of physics beyond the standard model. And my favorite candidate for that is a theory called supersymmetry. So I write it in big font just to convince you. And it's a theory which has fascinated theorists for many years. There's absolutely no experimental evidence for it, no direct evidence for it, although I would argue that the fact that it stabilizes the electroweak vacuum, the fact that it predicted correctly the mass of the Higgs boson, and that the Higgs boson would look like it does in the standard model, I would regard those as all being circumstantial hints that maybe supersymmetry is a good idea. And moreover, it can fix a whole bunch of other theoretical problems that I don't have time to go into, and it could provide the dark matter that fills the universe. So supersymmetry is, at least to us theorists, a very beautiful theory, and it's a very prolific theory. It predicts that every known particle is accompanied by another particle with the same internal properties, such as electric charge, but which spins at a different rate. And the lightest of those other particles could provide the dark matter. So let me just take out a couple of moments to talk about the dark matter problem. So this goes back to the 1930s. The Swiss astronomer Fritz Zwicky was observing the Coma cluster of galaxies, and he saw that the galaxies were moving around suspiciously fast. In order to hold those galaxies together inside that cluster, you needed additional gravitational field beyond that generated by the visible galaxies themselves. And he said, maybe in addition, there's another source of gravitational field that he called dark matter. So that was the 1930s. The 1970s, the astronomer Vera Rubin made a similar observation of the motions of stars in galaxies. She found they also move too quickly. They would also need some additional gravitational field to hold them together inside their galaxies. Again, evidence for dark matter. So let me just illustrate that problem. So here is a picture of the velocities of planets in our solar system. And they obey Kepler's laws. The further you are from the sun, the slower they go, basically because the gravitational field gets weaker because it's just generated by that sun sitting in the middle. But that's not what you see in a galaxy. In a galaxy, you see that the velocities of the stars and other objects orbiting the galaxy remain flat. They don't go down. They don't obey, apparently, Kepler's laws. You need additional gravitational field beyond that generated by the stellar disk and the gas, and that is the so-called dark halo, which would be made of dark matter. And then there's this picture, which I talked about the Large Hadron Collider. Maybe I should have called it the Little Collider. This is what may be the biggest collider in the universe. This is actually the relics of a collision between two clusters of galaxies, and they've just gone through each other. And in the middle, you see that red and yellow blob. That's gas. As the two clusters went through each other, that gas collided, heated up, and emitted X-rays. But those contours there, those show you the density of dark matter. Dark matter just went straight through. So there's this stuff that behaves in an essentially different way from the visible matter in the universe. So maybe it's made of particles. Maybe it's some sort of particle, like, for example, a supersymmetric particle, which interacts very weakly, doesn't have an electric charge, doesn't have strong interactions. So how would you detect it? So even if it has no electric charge or strong interactions, it must carry momentum. So what you do is you look for events where there's momentum being carried away from your collisions by invisible particles. So this is a simulation of the sort of effect that experiments at the Large Hadron Collider have been looking for. So on the right-hand side, you see towers of energy, momentum coming out on one side of the detector. And in the simulation, you don't see anything very much on the opposite side. So that event, transverse momentum, is not conserved, apparently. Of course, it must be conserved. It can only be conserved if there's invisible dark matter particles going on the other side. So the experiments have been looking for that. So far, no significant excess of such events, except maybe in a paper that was published a week ago. But okay, we'll see whether that holds up. So how else would you look for dark matter? Well, you could look directly for the scattering of dark matter in some deep underground detector, protected from cosmic rays. Particle comes through, deposits energy, which you can detect. But that hasn't been seen either. Star Trek. The reason why I mention this is because whenever CERN puts out a press release about antimatter, people get very excited. I'm not sure absolutely whether it's because of Star Trek or Angels and Demons. Well, we don't make enough antimatter at CERN to power up the Starship Enterprise or to destroy the Vatican. What we do is we study the difference between matter and antimatter. So as you probably know, Dirac postulated the existence of antimatter back in the 1920s when he combined special relativity with quantum mechanics. And he, and I think pretty much everybody else, expected that antimatter particles would be equal and opposite to regular particles, equal in mass but opposite in electric charge. Well, turns out that matter and antimatter are not quite equal and opposite. Some of their properties are different in a way that we don't fully understand, but it could be that that very small difference is related to the fact that in the universe as a whole, there's matter, but there's no large amounts of antimatter. So this could be the answer to Gauguin's question, where do we come from? And experiments at CERN and elsewhere are addressed to trying to understand whether that theory actually works or not. So this idea that the microscopic difference between matter and antimatter might be related to the cosmological abundance of matter, this is an idea that was proposed by the Russian physicist Sakharov, and here he is. He came to visit CERN in about 1990, so I think he's obviously checking whether somebody's explained the existence of matter in the universe yet. Anyway, according to his theory, you need this matter-antimatter difference, you need the expansion of the universe. So far, we haven't been able to fill in the details of his theory, but the basic idea, I think, is something that we certainly hold to. So finally, I want to come back to actually what was Andrew Chamblin's principal interest, namely quantum theory of gravity, which I had as number 7 on my list of the physics beyond the standard model. So of course, well, this is Albert Einstein again, a little bit older than in my first picture, maybe a little bit sadder, maybe because he foresaw that he was not going to succeed in making a quantum theory of everything. Well, maybe, but at least some of the ideas that he worked on are ideas which are nowadays very fashionable, in particular the idea that there might be additional dimensions of space has become very popular in string theory, which was one of the things that Andrew Chamblin was particularly interested in. In particular, he was interested in the idea that at the Large Hadron Collider, you might be able to make microscopic black holes. So here is a simulation of production of a microscopic black hole at the LHC. And I think he looks kind of cheerful about the idea. Other people were not so happy about the idea. Other people thought that maybe those black holes would eat up the entire Earth. Well, of course, that would not have happened. If we'd made one of those black holes, it would decay essentially instantaneously. It would not eat up the planet. And if you don't believe that argument, just remember those cosmic rays that have been bombarding the Earth for billions of years. I mean, they might have produced black holes, but we're still here. So there's no way that those black holes could be dangerous. So that brings me to the end of what I wanted to say. I hope I've convinced you that the Large Hadron Collider at CERN is not only the world's most powerful microscope, but it's also in some sense a powerful telescope, which may provide some more of the answers to some others of Gauguin's questions. Thank you.
So John has very kindly agreed to answer some questions. We've got a couple of minutes. Does anybody have a question?
This is what one there.
Okay, there's a microphone, so if you wait for the microphone and then go ahead.
Thank you for a very interesting talk. Now, before Higgs, we had no idea why various elementary particles had the masses that they had. After Higgs, we believe that the elementary particles possess the mass they have because of the extent to which they interact with the Higgs field. So in this respect, has our understanding of the origins of mass really been advanced?
So, so now we can tie the origin of masses to the existence of this universal field. Now, of course, you could ask the question, well, where does that universal field come from? And why does it have the value that it has? And why do some particles wear boots and other particles have snowshoes? So, what explains the difference between the various different particle masses? So we don't know. We've got lots of speculations about it, but we don't know, so there's lots of things for the young physicists in the front row to work on in the future. I think there was a question from the purple beret. Yeah.
Thank you, that was absolutely brilliant and amazing. I've got two questions. One's a rather flippant one. Why is there a disproportionately large number of Italian physicists?
I don't think anybody really knows about that. Some people say that it goes back in particular to Enrico Fermi, who was a very important and influential Italian physicist in the 1930s who moved to the United States and who somehow built up this whole sort of charisma attached to physicists. Then following the Second World War, there were a couple of other Italian physicists who had very high profiles, Nino Zacchicchi and Carlo Rubbia, so maybe they had something to do with it.
And I know this is really ignorant, but I don't really know anything about physics. So there is no quantum of gravity that's known about yet?
Not yet. So we firmly believe that a quantum gravity exists, so-called graviton, but it would be incredibly weakly interacting with regular matter. So if you had a graviton with the energy of a proton in the LHC, for example, you just couldn't detect it. So people are working on ideas for looking at quantum effects of gravity, and there's various ideas associated with black holes, with cosmology, but to actually detect a graviton particle looks very tough. Something else for the young guy in the front row.
Thank you.
There's a question in the middle.
Thank you. My question relates to the mass of the Higgs boson. One assumes then that the Higgs boson must interact with its own field in order to have mass.
Absolutely.
Which brings me to my question, which really has two parts. The first is, what is the nature of that interaction? And secondly, can one assume that each particle, whether it be a smaller particle or a larger particle, can interact with its own field And what are the results? Because I don't really hear much about the study of particles interacting with their own fields.
Okay, so indeed, there can be interactions between particles and their own field, what we call virtual particles. And so one of the big issues in theoretical physics, ever since Dirac basically has been trying to make sense of those calculations. And Dirac was one of the first people to actually confront this problem. Nowadays we think we have a way of calculating those effects, and in the standard model they give you finite results in general. Now, with regard to the Higgs, you're absolutely right. There is something which you might regard as being a Mercedes-Benz diagram, where a Higgs and a Higgs can produce another Higgs, and that is a self-interaction of the Higgs field. And we know that interactions of that type exist, for example, for the particles responsible for the weak interactions. But pinning down that similar sort of interaction amongst Higgs bosons looks very tough. Something which we hope we might be able to get some hint of with the Large Hadron Collider, but not immediately.
There's maybe a final question over here.
Just 2 points, really. Just in your thinking, in your thought, do you think this concept of dark matter being an operating system for the universe, do you think that's a useful concept in the way it's being presented?
So the dark matter?
Dark matter as an OS for the universe, an operating system for the universe. It's a computational sort of metaphor.
So, the idea of dark matter that I presented is incredibly conservative.
Oh, okay.
I'm just saying, let's take the same basic laws of physics, of gravitation, Einstein, relativity, and so on and so forth. And we just imagine that there's another particle. Right. That is really the least radical thing that you can do. I should say there are other people who say, throw Einstein out the window. There's all sorts of what I would regard as being slightly crazy ideas. What I presented was the most conservative option.
That's very honest. And just to clarify in my own mind, does the holographic principle and the holographic universe, does that hold hands with supersymmetry? Because I'm not up on that enough to know whether it's close enough to be connected.
Okay, so this idea of holography tells you that there's a relationship between systems in some number of dimensions and one smaller number of dimensions. It's an extremely powerful idea in theoretical physics, and in some sense it's emerged from thinking about quantum gravity and in particular string theory. But it's found applications in many areas like condensed matter physics. So I would regard that as being something which is sort of an outgrowth of these ideas about string theory and extra dimensions. Supersymmetry is something else which seems to be essential for string theory to make sense at a fundamental level. But so far we have found no evidence for supersymmetry.
Okay. Well, I'm afraid we have actually come to 6 o'clock, which is the magic moment. This has been absolutely superb. Thank you ever so much. Let's join once again in thanking Jeff.